7.2 is all about tangent lines and circles. We start the section with two definitions. Our first definition, a line in the plane of a circle that intersects the circle at exactly one point, is called a tangent line. Tangent lines actually also apply to other figures and also functions. In fact, in calculus, we begin our class talking about tangent lines a lot. But in any case, the tangent line is always the line which touches the figure once and only once. Next, the point where a circle and a tangent intersects is called the point of tangency. Underneath, we have a diagram of a circle and a tangent. The line AB is called our tangent line, whereas the point B, where it hits the circle, is called our point of tangency. If a tangent line touches in more than one point, it is no longer a tangent and it becomes a secant line. Okay, we move on to two theorems about tangent lines. So our first theorem states that if a line is tangent to a circle, then the line is perpendicular to the radius of the point at the point of tangency. So we see in our picture we have a tangent line AB, and what it's saying is that AB will be perpendicular to OP. So line AB, our tangent line, will be perpendicular to our radius OP. Our next theorem seems like it says the same thing, but it's actually the opposite, the converse. If a line in the plane of a circle is perpendicular to a radius at its endpoint, then the line is tangent to the circle. So what they're saying here is that if you have a line which is perpendicular to the radius, then it's called the tangent line. So then in this conclusion, we would state that then line AB is tangent to circle O at point P. Okay. In this section, we're going to use these theorems to apply to various problems. Each problem will be a little bit different, and we're going to actually use a lot of information that we used in the past. Most of it, or I should say all of it, is going to stem back to right triangles. So I handed out to everyone in class a reference sheet of things to remember, things that we're going to use in these sections. And I'm just going to expect you to be able to recall these things. So it might be helpful to use this reference sheet at least at first, but then hopefully be able to do these problems without it. So we have special right triangles that we're going to use in these problems, trigonometry, as well as the Pythagorean theorem. Keep in mind, with the Pythagorean theorem, we have two known sides and we're looking for the third side. Special right triangles in trig, usually we have an angle and a side and we want to know another side. With special right triangles, that angle should be one of our special angles, a 45 or a 30 or a 60. Whereas trig is going to be any other angle besides those three. So let's take a look at how we would apply these theorems. So in number 1, we're given a tangent line. So since we have a tangent line, according to the previous theorems, that means that we have a right angle. And the reason why that theorem is helpful is because now, if we look at our diagram, since this is a right angle, we have a right triangle. And all of those things on our reference sheet come into play. We know that the radius is 5, and we know that segment BD is 12 as marked in the picture, and we want to find ED, this segment right here. So how could we do that? Well, as I had mentioned, we have a right triangle. And something important is in a circle, all of our radii are congruent. So what does that mean? Well, if you notice, the radius is 5, so that means AB should also match the other radius in the picture, AE, which means that this segment right here is also 5. So every single side has been marked with something. Since I have no additional angles beyond the right angle, this is actually leading me to the Pythagorean theorem. So let's go ahead and set up the Pythagorean theorem for this problem, and hopefully we'll be able to solve for x. So the Pythagorean theorem is a squared plus b squared equals c squared. The most important side to fill in the Pythagorean theorem is the hypotenuse, the c. So let's fill that one out first. That would be the side across from the right angle. So the side across from the right angle would actually be AD. So what's the length of AD? It's not 5, it's not x, it's actually those two segments together. So since it's those two segments together, that whole distance will actually be 5 plus x. And that's actually going to go in for C. Now notice, since that's a binomial, I have to put parentheses around it before I put the square in, because the square applies to the entire quantity. Now your other two sides of the right triangle, the 5 and the 12, will be your A and B, and it doesn't matter which one goes in for which at this point. So I'll go ahead and just fill in 5 squared plus 12 squared. Okay, so we want to solve for x. So what I'm going to do first is I'm going to simplify all of the numbers that can be squared. So 5 squared becomes 25, 12 squared is 144. And on the right, you could actually FOIL this out, but it's going to make a trinomial, and since I only have one x in there, I'm going to leave it as it is right now. Okay, I'm going to continue to solve, or simplify I should say, the numbers here. So 25 plus 144 would give me 169. As I had mentioned before, since I only have one x in this entire equation, I'm now going to start to peel off all of the layers to get to that x and solve for it. So on the right-hand side, I've got the 5 and I've got the squared. We always deal with the outermost layer. In this case, that would be the square. So to get rid of a square, we're going to undo it with a square root. So we're going to take the square root of both sides. The square root of 169 will be 13, and the square root of the square are essentially inverse operations, and will just leave us with 5 plus x. Now, something interesting to note, when you take a square root of an equation, you actually have two roots, a positive and a negative. So we actually have to consider both of those values. So we're going to add plus or minus to the 13. So this actually gives us two different equations at this point. We have positive 13 equals 5 plus x. Oops. And we have negative 13 equals 5 plus x. And we're going to solve each equation. So for our first equation, we're going to subtract 5 to both sides, and we get a value of 8. For our second equation, we're also going to subtract 5, and it looks like we get negative 18. So we get negative 18 and positive 8. Now the thing is this is representing a segment length. It doesn't make sense to have a negative segment length, so we're actually going to eliminate this second answer because it doesn't make sense for a length. And that would give us just one single answer of 8. And we could go back and plug it in here, and if we do, we would find the whole length AD to be 13. And we could check to make sure that that is indeed a right triangle by doing 5 squared plus 12 squared and checking to see that it's equal to the 13 squared, which it would be. So let's take a look at another example. Number 2, solve for BC given AB is a tangent to the circle. So once again, since we know that we have a tangent, essentially the theorem is only telling us that there's a right angle there. But now that I have a right angle, I have a right triangle, and I can just use all of the stuff from my reference sheet, either Pythagorean theorem, trig, or special right triangles. So here I have one angle and one side. Since I only have one side and I don't have two, at least two I should say, Pythagorean theorem really isn't going to help me a whole lot here. So this is probably going to be special right triangles or trig. And if I look at that reference angle, 25, that is not one of our special angles, so this is probably going to be a trig problem. Okay, so I'm looking for BC. So BC is going to be my x. So let's go ahead and first mark the unknown with our variable. And technically I could have marked it any variable I want, but I guess we are traditionally using x. So with trig, if you recall, we're going to label all of our sides first. So I like to label my hypotenuse, the side across from the right angle. And then I usually do the opposite side across from the reference angle, 25. So that would be x. And the adjacent side will be the leftover side. Then if you recall from trigonometry, I circled the two sides that I have information or want information about. So I have the 7, so let's circle A. And then I also have the, or I should say I want the x side, so that's our O. So we have O and A. So let's go ahead and take a look at our reference sheet. When we have O and A, that would put us into a TOA situation. Then we're going to write our equation, which if you look at our reference sheet is going to be a trig function, which for TOA would be tan, of the angle, which is 25 in this case, and it will be equal to the second over the third letter. So in TOA, it's going to be opposite over adjacent. So that's what our reference sheet is telling us there. So let's go ahead and write that equation for this problem. Once again, we're in TOA, or we're using TOA, I should say. We start with the trig function, so T represents tan. We have our angle, 25, and it will be equal to the second over the third letter. So the opposite, O, x, over the A, the third letter, 7. Once we have our equation set up, we're going to use one of the three methods for solving an equation. And again, I'm going to go ahead and turn to my reference sheet because I've depicted all three methods of solving a trigonometry equation. Here we have the x in the numerator, so this is actually going to be a case 1. So when the variable is in the numerator, we're going to simply multiply by the denominator to solve for that variable. So let's go ahead and do that. Let's multiply by 7. And in doing so, we get 7 tangent of 25. And that will be equal to x. Okay. Let's go ahead, I'm going to use my calculator here and type in 25. We need tangent of that, and then we're going to multiply that by 7. And that would be 3.26. And that would be x, and that would be the side that we're looking for. Okay, awesome. In example 3, we want to find the radius of circle C. And once again, our symbol for circle did not show up. So if it's not on your notes, go ahead and fill it in at this time. So let's take a look at the picture. We have a tangent line, AB, even though they didn't tell us it was a tangent line. I knew it was a tangent line because it had a right angle. Because as you know, if it's a right angle, then it's a tangent line. If it's a tangent line, then there's a right angle. And since we have a right angle, we have a right triangle, so I can pretty much ignore the circle itself and just think about the three methods for solving a right triangle. We have Pythagorean theorem, trig, and special right triangles. So it looks like there is no additional angle besides the right angle, so that actually automatically rules out special right triangles and trig since we need that extra reference angle. And this is leading us to Pythagorean theorem. So let's go ahead and use Pythagorean theorem again. A squared plus b squared equals c squared. For Pythagorean theorem, once again, I like to fill in my c, my hypotenuse, which is always across from the right angle. In this case, it's going to be the segment AC. X plus 8. So once again, we have a binomial for our hypotenuse. So you need to put it in parentheses before you square it, so that the square applies to both terms. That leaves your x and your 12 as your remaining two sides, or our a and b for the Pythagorean theorem. Okay, so let's simplify what we can. So x squared can't be simplified, but 12 squared could be 144. And we can't simplify, well, I shouldn't say we can't, but the question is, do we want to simplify x plus 8 quantity squared? Now, in problem number 1, I didn't simplify because there was only one x on the right-hand side. But here we actually have two x's. So I actually want to simplify this one and distribute it further to see what happens. So in order to distribute a binomial squared, you're actually going to think about it as a binomial times itself. So x plus 8 times x plus 8. And when you have a binomial times a binomial, to distribute, you may recall the magic math word FOIL, first, outer, inner, last. So let's go ahead and FOIL this binomial times this binomial. So the first terms, x times x, would give us x squared. The outer terms will be next in FOIL. So x times 8, or 8x. The inner terms, 8 times x, 8x. And the last terms, 8 times 8, 64. If we continue to simplify the right-hand side by combining like terms, you'll notice that I get x squared plus 16x plus 64 because our two 8x combined together to get us that 16x. Okay, so what do we do from here? Well, when I have variables on both sides like I do here, I like to get rid of one by subtracting it. So I have an x squared on the left and an x squared on the right, so I'm going to get rid of one by subtracting it. So let's suppose that I want to get rid of the one on the left. So let's go ahead and subtract x squared. But when you subtract a term on the left, you have to subtract a term on the right as well. What happens is the x squared cancels on the left, giving you 144, and wait a second, the x squared cancels on the right as well, leaving me with 16x plus 64. Look at that, the x squared terms just completely went away, leaving us with one single x to solve. Isn't that convenient? So let's solve for that x by getting rid of the 64, subtracting it, and we get 80 equals 16x. And then last but not least, solving for x by dividing by 16. And 80 divided by 16 will give us 5, giving us a final answer of x equals 5. Awesome. One last problem. Number 4. Is segment ML tangent to circle N at L? Explain. And once again, our circle symbol is missing, so you can go ahead and fill it in. All right, so how are we going to tackle this one? Here we have all of the sides. We have our 7, we have our 24, and 25. And I'm assuming that this 25 is actually going to the entire segment M and N. Okay, if you have any questions about any numbers and what segments they're labeled, you can always ask, just to be certain. Okay, so how are we going to do this? Because we already know all of the segments. How would we know if it really is tangent? Can I say yes because it looks like it? No. In geometry, you can never assume things just merely by their looks. So we have to prove it. And we're going to prove it by one of our theorems, which states if it's a right angle, then it's tangent. So how can we prove that there's a right angle here? That's the question. Well, you can prove that a triangle has a right angle by showing that the Pythagorean theorem is going to be true. So essentially what we're going to do is we're going to check our a squared plus b squared equals c squared and see if it is indeed true. So let's plug in what we know. Our hypotenuse is the most important side, which is across from the supposed right angle, which would be our 25. And that leaves our 7 and our 24 as our a and b. Simply simplify the left and the right and see if they're equivalent. So 7 squared gives us 49. 24 squared, I've calculated ahead of time, it's 576. And 25 squared is 625. Adding the left side up, 49 plus 576, we get 625. So, since the left is equal to the right, the Pythagorean theorem is true, therefore there's a right angle, and therefore by the theorem, this is a tangent line. So yes, ML is tangent because the Pythagorean theorem is true. And you could even say, and also by the theorem that makes the tangent line, or sorry, that makes the segment a tangent line if there's a right angle. And that's the end.